Welcome to day 3 of electromagnetism. So this one we're looking at something called magnetic induction. So these two guys, Hans Christian Ørsted, he discovered that current produced a magnetic field. Later along, a guy called Michael Faraday came around and found out that you can produce a voltage or a current using a changing magnetic field. So it's not as simple as just having a magnetic field in the presence of like a wire or something. A current is only produced if there's a magnetic field that's changing. So hopefully you had a chance with the solenoid. So if we had a solenoid, if you had a magnet and just placed it nearby the solenoid, nothing actually happens. However, if you move that magnet closer to the solenoid or further away, like while the magnet's moving, you may have seen a current produce. So this is a very simple circuit. We have what's called a galvanometer. It's a more sensitive ammeter that can measure alternating current because it'll swing back left to right, left to right. So for example, if you brought this magnet towards the solenoid, you see a current produced in one direction. And when you brought the magnet out of the solenoid, you see it swing back the other way. So we call that alternating current. When the magnet's stationary, again, we would see no current. So we need a changing magnetic field. So let's just draw this out. So first I want to make sure we understand the situation. Let's say we have a loop of wire. So here's a three-dimensional picture. So if we have like some loop of wire and a magnetic field passing through, so it's going through the space. So we have a magnetic field going through. Okay. So flux is based on how much area there's going to be and the strength of the magnetic field. So that what we call this magnetic flux, the magnetic field passing perpendicularly through a unit of area. Faraday observed that EMF did not depend solely on the rate of change of B, but something called this magnetic flux. And similar like the electric field, we think of these lines. The more dense these lines are together, the greater the magnetic field. So think about another way of thinking of magnetic flux is think there's a rainy day. There's two ways to get greater flux. Let's say rain falling in a bucket. If you have a small bucket and rain falling, right, rain falling around, our flux of water passing through the opening of the bucket would be very small for a small bucket. But if you had a bigger bucket also placed outside, the flux is a lot greater because more water can enter that bucket. Again, another way to increase the flux is if you have like more rain, so a really rainy day. So we have an equation for flux. We use this symbol, and this is equal to the magnetic field, and that's perpendicular to the area. So we can also write it as BA cos theta, depending on where you're measuring the angle. So it's either sine or cos depending on where the angle is being measured from. So for example, let's say we have some type of surface area and we have magnetic field lines coming in like so. If we measure that angle relative to the normal, it would be cos. If it was along that plane, it would be sine. So area in this case would be just L times L. And just the strength of the magnetic field, B. So the units for flux is equal to Tesla meters squared. And we also call that the Weber, W-E-B-E-R, the Weber, W-B.